Welcome back to this channel. My name is Dr. Arzu Jabra, and I have a PhD in organic chemistry. I am an organic chemistry tutor, and um, I am also an academic mindset coach for college students. So, besides teaching organic chemistry, I help stressed out, overwhelmed students to go from overwhelmed to feeling a lot more focused, excited, and be more in control of their time and their energy. So today we are working on the fourth chapter of MCAT Kaplan Orgo problems. And that's what we're going to be solving. I am going to be solving today. And again, the PDF for the PDF document, which contains all the problems, will be linked down below. And if you want to go over the problems, double check your answers or the explanation from my video, go for it. And let's get started here. And let me share my screen really fast. Today we'll be solving alkene, alkynes, um, and is there anything else? Alkene, the chapter Alkene Alkyne. I forget. This is chapter 4. I think there's one more topic to it. I think there is a one problem which is about substitution reactions, I think. Oh yeah, I think elimination. It covers some of the elimination reactions. All right, regardless. So let's get started and solve these problems. And of course, if you have any questions whilst I solve it, and leave it in the sometimes I have like two thoughts at once, and it just makes it worse because then I'm like saying confusing like two sentences or saying two sentences at once. So I was saying that if you have questions, feel free to leave it in the comments. And of course, if you want me to explain any of the problems in detail, also leave that in the comment. I would be very happy to help. Of course, if you want to email that to me, feel free to do that on the email linked down below. And another way of actually solving this problem, my second thought was that you can just look at the problem, pause the video, get to the answer, and then double check after I have explained the answer. If you get the incorrect answer, come back here and then understand why it was incorrect so you can get a better explanation of this answer. So that's like another way of actually approaching these problems. All right, so what is the major product of the reaction below? Okay, so this is the first problem, and what we have here is an alcohol. Okay, so we are starting off with an alcohol, and we have H plus and heat. And so we do know that adding an H plus to an alcohol is a really good method of converting an OH, which actually is a bad leaving group, to a good leaving group, because in the first step, right, when you add H plus, it becomes water, right? OH, H. So it becomes water, and then we do know that now it is H2O, and H2O is actually a really good leaving group. However, OH is not a good leaving group, okay? And then when you heat this reaction up, we do know that heating the reaction up or adding heat allows for elimination to occur, favors the elimination reaction, right? And that is why when we start off with this reactant and heat it up, so it favors elimination or substitution, right? And if we think about it again, in the elimination process, there are two types of products that are favored. One is the Hoffman product, and other is the Zaitsev product. Okay, but then because there isn't really a base that's actually being used for the elimination, so we're not really dealing with bulky base versus non-bulky base. We're just really dealing with heat. So then in this reaction, right, where an E1 type of elimination would be favored, or yeah, so then a more substituted alkene would actually be favored in this reaction, right? Because a non or a bulky base is not used here. So only when a bulky base is used, then a Zaitsev product becomes the more favorable product, right? So right now it's just under heating conditions. So right now a Hoffman product would actually be a more favored elimination product, right? So now this is our Hoffman product, and the other one would have been the Zaitsev product. So if a bulky base was used, then a Zaitsev product would have been favored. Right now, only a, what is this called? Hoffman product is favored. So this would actually be the product of this reaction. And now if you think about it, what the nomenclature, right, for this reaction is, or this product is. So what we really have here is 1, 2, 3, 4. So we have butene. So we actually have like 2-methyl, right? 2-methyl butene. Sometimes 2 is also brought to the front. So it's actually 2-methyl 2-butene, which is actually option D. All right. The above reaction takes place mostly by which of the following mechanisms? We know this is a 3-degree carbon center. 3-degree carbon centers favors E1 and E2 both. Okay, so when we look at the product is an elimination product. It's not really SN1 or SN2. So it's mostly E1 or E2. They're wanting you to identify whether it's E1 or E2, right? We know that for an E1 reaction conditions require you to actually have a weak base, right? And heating conditions. However, in E2 reaction conditions require you to have a strong base and heating conditions. So if you think about the reactants over here, we have CH3O minus, which actually is a strong base, right? Because there is a negative charge on it. So strong nucleophile and a strong base. So then E2 is the correct answer for this problem. Just really quick, really fast, H2SO4, when an alcohol is used, if the reactant was an alcohol, and if H2SO4 is used under heating conditions, boiling conditions, right? The product is actually an E1 mechanism product because H plus in the first step, OH takes the H plus from H2SO4, right? So then in the first step, the reactant becomes OH2. So now we have water, which is a good leaving group. So finally, the reaction can actually happen in E1 or E2. And then in the second step, the HSO4 minus is actually then used as a weak base to cause the elimination, right? So now, again, like we said, E1 category of the reaction requires you to have the weak base, and HSO4 minus is actually a really weak base, even though there's a negative charge, but it's actually one of the really weak bases if you'll draw out the structure, and I'm not going to get into that right now. But using H2SO4 and heating conditions with alcohol as the starting material is a classic E1 mechanism. This is a heat, which is delta, it's not a D. It's a classic E1 mechanism problem. So just like to always keep that on top of your mind, that is E1 category will kind of be helpful. All right, which of the following products would be formed if 2-methyl 2-butene were reacted with hot basic KMnO4? Okay, so what we're really thinking about here is which of the following products would be formed if 2-methyl 2-butene, okay? 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. So we've got 2-methyl, okay, 2-butene. ene. Okay, so we are now here. Were reacted with a hot and basic KMNO4. Okay, so hot and basic KMNO4 is different, right, from cold KMNO4, because if you have cold KMNO4, the reaction conditions are different, and then you will form different product. So you have to keep in mind that the KMNO4, that the oxidizing reagent that's being used, potassium permanganate, is under hot conditions. So then if you really think about it, hot KMNO4 does an oxidation reaction, oxidizes and fragments your alkene to fragments alkene to the most oxidized product possible. And what that really oxidized product possible, meaning that oxidized product possible, what that really means is that if you're able to actually form, right, if you're actually able to, so we fragment the alkene first of all, and if a ketone is the most oxidized product that you can produce from that fragmentation, then that is the product of that fragment of that alkene. And then for the other fragment, if you're able to oxidize it to a carboxylic acid, because that's like the most oxidized possible product with an oxygen, or the functional group with the oxygen, right? So when we break here, if you think about it, we already do have like 2 carbons, right? And we do know when we add the oxygen, it's always first added with a double bond. So we can really only actually get from like left fragment, we can actually only get a ketone, because if we were to form a carboxylic acid, right, then we would have to form this product, but then this carbon doesn't allow for adding that extra OH here. So when you have 2 carbons, almost like a bi-substituted alkene on that second carbon, then in that case, you can actually only form the ketone, right? You can actually only form the ketone as the most oxidized product. But however, if you look at the other side of this fragment, now over here, we do really see that we have only 1 carbon right now. Then on this side of the fragment, we don't have a carbon. So when we actually oxidize it, you can make a C double bond O and also an OH. So this fragment, or actually the second fragment of that alkene, can be fully oxidized. So the products of this reaction are going to be that ketone and also C double bond O, OH. Okay. So then the products of this reaction are acetic acid and 1 mole of acetone, right? Because this is acetic acid. Acetic acid is same as ethanoic acid, like an acid of 2 carbons and an acetone. All right, perfect. The next question. What are the products of the following reaction? So now in this reaction is ozonolysis reaction. And if you really think about like the shortcut of solving this problem, right? Again, just like HMNO4, we oxidize and also under reducing conditions. So we do see this is under reducing conditions and not under oxidizing conditions, right? Oxidizing conditions are if they add acetic acid, CH3COH, which is oxidizing conditions. But right now they're just using reducing. If they have zinc, that's a metal, right? It's a good reducing agent. So it is under reducing conditions. So the reaction under reducing conditions is as follows, that we break the double bond over here, right? When you break this double bond over here, okay, again, it's a fragmentation reaction. You fragment the bonds of alkene just like we did under hot KMNO4 conditions. And then in the next step, right, we just add a double bond. Oh, we add only a ketone to each carbon of that alkene. So effectively, the products that we are forming is right? For the first product, we formed an acetone or a ketone. Now for the second product, we have only C double bond O, right? Because there's only one carbon over here, and we're adding the double bond O. This is the ozonolysis reaction. And then you add the hydrogens to both ends of that carbon, and then that is your other product. So that actually is called formaldehyde. This is a formaldehyde, right? Because it's actually an aldehyde with one carbon, and this is an acetone. So let's look at what are the possible options for this answer, which matches what we have here really fast. So D is the one that we actually got. So D is the correct answer for that problem. All right, next problem. What are the products of the following reaction? Now we've got an alkyne and hot cheminophore under basic conditions, right? OH minus is base. Again, they have hot cheminophore and not cold cheminophore. So this for this reaction, right? So then we've actually got an alkyne and okay. So we've got we have an alkyne, right? And when you do the same process on alkyne, what we know is that alkyne can not usually really have at the carbon of the alkyne, it cannot really have two carbons bonded to it. So it cannot really be di-substituted like an alkene, right? So both the carbons of that alkyne can get fully oxidized. At each carbon, you can form the carboxylic acid, right? What I really mean by that is when we fragment the bond, the triple bond, right, at 1, 2, at like the second carbon of this alkyne, we can actually form C double bond O, right? And can also do an OH. So think about like when we actually fragment the triple bond, right? So think about the fact that the triple bond like no longer exists. So then we actually have two fragments. So one of the fragment is like CH3C, and the other fragment is also C, CH and CH3, CH3. So now because we know that this carbon only is attached to one carbon, every carbon will form 4 bonds to maintain its octet, right? So then you can actually form 3 bonds. One of them is a C double bond OH, right? To form the carboxylic acid, so fully oxidized product. And then the other carbon also can actually be a C double bond O fully oxidized. So this is the magic when we have a triple bond and not a double bond, that when you have a triple bond, it can, on both the fragments, it can get fully oxidized. But that may or may not be true, just like what we saw right now for an alkene. It may or may not be true for an alkene. So when it's di-substituted, we stop at the ketone oxidation. But when it's mono substituted alkene, right, then we fully oxidize it. Oh no. Okay, I'm back. So then we fully oxidize it to carboxylic acid. So it all depends on how many bonds it originally has on the molecule. So if you really think about the product, so what I see, the one that matches with what I got is actually compound C. So then C is the correct answer for this problem. Okay. Which of the following represents the product obtained in the above reaction? Okay, so if you think about it, we've got HBr, peroxides. So then in this reaction, actually, we are adding HBr, right? So we are adding HBr, and what we know is when you have peroxides, HOOH, so this is hydrogen peroxides. It can be any peroxides, but addition of HBr in the presence of peroxides, you got to know that it actually is an anti-Markovnikov addition, right? This is an anti-Markovnikov addition. Because it's that, then the addition of HBr happens. The Br adds on the Br gets added onto the right over here, right? So the last substituted carbon the H gets added to the more substituted carbon, so like that. So then A would correspondingly be the correct answer for this problem. All right, let's get to the next problem. What is the major product of the reaction shown below? So what we do really say here is the Lindlar's catalyst. Before you solve this problem, again, you have to know from memory that when you do hydrogenation using Lindlar's catalyst, this catalyst does not undergo full reduction, right? So this is adding hydrogen. Addition of hydrogen is a reduction reaction. And when we use the Lindlar's catalyst, right, then it converts your alkynes to an alkenes and not all the way to an alkane. So the only reagent that can convert your alkyne fully to an alkane is hydrogen. And when they use platinum or nickel as a catalyst or as a metal catalyst, right? A lot of those metals can actually be used, like rhodium, sometimes iridium for hydrogenation. I had one of my projects in my PhD was carrying out the hydrogenation under very, very high pressure. That was one of the reaction I was studying and optimizing. So alkyne to alkene is actually a using Lindlar's catalyst. So this doesn't do full reduction, right? Here's the other thing that you have to remember, and that is that it is selective for Z products, right? Meaning that when this is going to form alkane. I'm gonna fully write the reaction. So when we start off with an alkyne, and when you use the Lindlar's catalyst, right? Then the product is actually Z selective product, meaning that a cis alkene is actually formed in this product. However, when you use sodium in ammonia, right, that product or that reactant or the reagent is actually E selective, meaning then you form trans alkene over here. However, with the Lindlar's, it is selective for Z product. So this is a Z selective or more like cis alkene would actually be formed. And I do already see Z to pentene. Of course, I want to double check, make sure, right, that that's the product that I'll be forming. So if I form the product, it would actually look like this. And if I count 1, 2, 3, 4, 5, if I do have 5 carbons, right? So I am forming Z, right? This would actually be a Z alkene. 1, 2, 1, 2. Okay, 3, 4, 5. So we've got Z to pentene, right? Cool. All right, so Z2 pentene, problem A, part A is the correct answer. And of course, you just don't want to look at A, right? Sorry, Z, and then just answer the question right away. You just want to be a little bit more mindful, because what if like one of the options is like no correct answer? Because they can give you that too. Like what if they had said Z2 hexene, and that wouldn't have been your correct answer, right? So you do want to make sure not just Z, you're not just like choosing that because it says Z on it, but also the correct number of carbons. All right, next problem. Given the reaction below, what is the major product? Not counting stereoisomers. So they don't really want you to look at cis or trans or R and S, sorry, stereoisomers, right? What is the major product of the reaction? So if we look at the reaction, this is the chapter dienes, right? When you have not just an alkene, but the addition on dienes, the ones that are conjugated. And what we know about this reaction or this reactant is that these reactions can be of 2 types, right? You can do the reaction at -78, or you can do this reaction at 0 degrees Celsius to room temperature. So like somewhere which is still warmer temperature, right? 0 and room temperature. -78 is crazy low temperature. So when you do the reaction at -78, right, that is a kinetic product, right? There is no rearrangement that happens, meaning that when we form the product, we just form the product via one of the double bonds of the alkenes, and there is no rearrangement in the reaction. However, when you form the reaction, when you do the reaction, carry out the reaction at temperatures that are like 0 degree, not too cold, all the way until room temperature, they have the possibility of undergoing rearrangement. So then they undergo the rearrangement, actually form a more stable thermodynamic product. But right now we are looking at the kinetic product of the reaction. So if we look at all the options over here, right, then we do see that for option A, this is actually incorrect answer, because you can never actually have two BRs on the same carbon when we are doing the reaction of the addition reactions on the alkene. Now, if we really think about option B, we have these two, the BRs actually getting added on the double bond, and only one of the double bond is getting affected. So this over here is a rearranged product, which is actually the thermodynamic product, right, of that alkene. So this is actually the kinetic product. Only one of the double bond is reacting. So B is the correct answer. And if you think about D, which is incorrect completely, because they cannot really retain the double bond and add BRs on it at the same time. So B is the correct answer for this problem. Okay. Which of the reagents shown below will furnish 2-butanone starting with either 2-butyne or 1-butyne? So meaning which of these options, kind of misaligned over here, A and B is more towards the right and C and D are kind of on the left. So which of the reagents shown below will furnish 2-butanone starting from either 2-butyne or 1-butyne? Okay, so when we're starting off with 2-butyne, 1, 2, 3, 4, versus 1, 2, 3, 4, just the positioning of the triple bonds are different, right? So the triple bond are over here at the second position, 1, 2, 3, and the triple bond is at the third position for this one. Sorry, actually, I should probably just say the first position, right? Because that would be the correct numbering. So which of the following reagents shown below will furnish that product? From both the sides, you should be getting one product, right? And what reactants should actually be used. So for option A, we have H3O plus and water. If you do that, it's just you're just using acidified water. So you're adding the acid and then carrying out the hydrolysis. Think about option B, we have BH3THF. It's just adding a anti-Markovnikov, adding a C double bond O. So the less substituted carbon, what should actually get the less substituted, right, should actually get the double bond O. And BH3THF, okay, the double bond O actually, so that would be incorrect because we want the double bond O over on this side. Okay, and oh, sorry. Oh, I totally forgot. So it's we actually add the OH. This is like the addition, right, of HOH. And this is also the same thing, right? The addition of H plus and kind of OH minus. From the water, you will get the OH. So if we actually use option A, right, then in that case, we're going to get the OH over here and H over here, acidified. Acidified water in the first option. So that is going to give us an OH over here with the double bond. And if I rearrange that, so you would get double bond O and the carbon over here. That would be the rearrangement. Okay, I think there's something wrong here. I think with the acidified water, right? Acidified KMNO4 is just for oxidation. And if you think about the option D is also what we're going to get. That's also a Markovnikov addition to the product. So again, if we have Markovnikov addition, we're going to get these products. So which is actually, again, adding the OH over here and H over here, right? So I feel like A and D are going to get the same products. Um, however, there is something I feel D is actually the correct answer, but I'm just thinking why not A? So because we're just adding acidified water again, right? Because so the first step there is H plus, and adding it on an alkyne, if you add the H plus, it's an addition reaction. The first step of the reaction would just be grabbing the H plus, and okay, so we are going to grab the H plus and form the carbocation over here, which is not a very stable carbocation. The water will attack over here. To get the OH. So I think A and D both should be the answers, but I think I have to double check. I feel like D is the only answer, but I think I'm missing out a nuance on that, and I will. Okay, I'm gonna pause here and just double check like why A is not the correct answer. I think I'm just um missing something, an important point. So I'll restart in a sec here.